In this lecture, we'll discuss another concept that is associated with square matrices, real square matrices, and that is minimal polynomial. So, what is a minimal polynomial? So, suppose the characteristic polynomial of a matrix, let's say A, which is n cross n matrix. We have been denoting it as this. We've been denoting as this. I'll try. I like to correct this symbol. Instead of this, we'll denote it possibly like this: characteristic polynomial of matrix A, where lambda is the eigenvalue of the matrix. Okay, and this is what we said, that it is nothing the determinant of lambda in minus A. Okay, so let's say that A has some eigenvalues, and the eigenvalues are, let's say, lambda 1 with algebraic multiplicity being n1, lambda 2 with algebraic multiplicity being n2. Similarly, if we continue writing, we'll have, let's say, lambda m with algebraic multiplicity nm. Okay, such that summation j equal to 1 to m nj is equal to the order of the matrix or the degree of the characteristic polynomial. Okay, nj is basically the jth eigenvalues algebraic multiplicity. Okay, so let's say this is what we have. Then essentially, so from here I can express this characteristic polynomial as a continued product. I'll say j equal to 1 to n, and this, so lambda minus lambda j, where lambda j is basically a root of the characteristic polynomial. So lambda minus lambda j becomes the factor, and the algebraic multiplicity basically tells you how many times lambda minus lambda j is repeated. So this is what actually you have. Okay, now we represented the geometric multiplicity of jth eigenvalue with the symbol nj bar. Okay, now number of Jordan blocks that are associated with the eigenvalue or the jth eigenvalue, that is also same as the geometric multiplicity, and hence nj bar. Let's say that the size of the largest Jordan block corresponding to the jth eigenvalue, let us call that as, let's say, mj. Okay, so this m and the m that we used upstairs with the continued product or the summation, they are different. Okay, So the size of the largest Jordan block corresponding to the jth eigenvalue is mj. For example, if I consider a matrix A whose Jordan form, let's consider a matrix A which is of this form. Let's say lambda 1 0 sorry, lambda 1 0 1 0 0 lambda 1. Then let's say you have this. So here if you see, there are two blocks corresponding to the eigenvalue lambda. So what we have, n1 is 4, this is the algebraic multiplicity. N1 bar is what, 2, because there are two Jordan blocks. And M1, so if there are two Jordan blocks, one has a size of 3 cross 3 and another has a size of 1 cross 1. So M1 in this case would be 3. Okay, so this is what that M1 relates to. So or MJ relates to. This is the size of the largest Jordan block corresponding to the jth eigenvalue. So collect all the Jordan blocks that you have corresponding to the jth eigenvalue and find what is the largest size largest size available from the Jordan blocks. Okay, that is MJ. Now, once you find this number MJ, let us consider this as a symbol and construct a polynomial like this. J equal to 1 to m lambda minus lambda j to the power mj. So what I am doing is I am considering the largest size of the Jordan block associated with the jth eigenvalue. I am taking the factor lambda minus lambda j and raising this to the power of raising this by a power of mj, and I do this for all the eigenvalues that I have in hand and take a product of them. That results in a polynomial. Okay, please note that the characteristic polynomial, I'll make a small remark here, the characteristic polynomial, or what we have been using delta this, and the polynomial that we are talking of ma lambda are monic polynomials. Monic polynomials, which means the coefficient associated with the largest power of variable in the polynomial is 1. Okay, so these are monic polynomials. So the polynomial that I am forming here as ma of lambda is a monic polynomial. Okay, so if I take another example to illustrate this, let's say that a is, let's consider 6 cross 6 a. Let's say it is lambda 1 1 0 lambda 1. Okay, I'll put rest of this as 0. Let's say this is what I have. this is the matrix that I, let's say, have in hand. So this is already in its Jordan form, and you can note that the eigenvalues are lambda 1 and lambda 2. For lambda 1, n1 is, how many times it is repeated? 1 2 3, so it is 3. Similarly, the algebraic multiplicity, or n2 for lambda 2, is 3. It is repeated thrice. Now comes the geometric multiplicity. So n1 bar, you see how many uh, Jordan blocks do you have with respect to lambda 1? It is 2. So n1 bar in this case would be 2. And how many are associated with lambda 2? There is only one Jordan block that is associated with lambda 2. So n2 bar is 1. Now what is m1? M1 is basically, you see there are two Jordan blocks. One is of size 2 cross 2, another is size 1 cross 1. So the largest size is 2. So M1 is 2. Similarly for M2, there is one Jordan block whose size is 3 cross 3, and that is the largest size that is associated with lambda 2, and hence M2 is 3. Okay. Now the characteristic polynomial that you get will be of this form: lambda minus lambda 1 to the power 3 multiplied by lambda minus lambda 2 to the power 3. But the MA polynomial that you get, that is equal to lambda minus lambda 1 to the power 2, because m1 is 2, multiplied by lambda minus lambda 2 to the power 3, because m2 is 3. Okay, so this is the difference between the characteristic polynomial and the polynomial MA that we have. So from here you can note that MA polynomial is a factor of the characteristic polynomial. Right. So this is what you can immediately observe from here. Now, what is so special about this MA polynomial? So the specialty about the MA polynomial is the following. If you replace lambda with the matrix A, then this polynomial of the matrix, I am dropping the subscript A, this polynomial of the matrix is essentially A minus lambda 1. Of course, this gets associated with the identity matrix In squared for the example that I am taking, and A minus lambda 2 In cubed. So this is what you actually get. Okay, replace lambda with A, then MA polynomial is essentially a matrix polynomial now, and you get this. Now this turns out to be a zero matrix. Okay, you can verify this. This can be proved. I am skipping the proof as of now, but this is what you get. Okay, so in general, if I substitute MA in place of lambda in the MA lambda polynomial, then this is nothing but equal to the zero matrix. Okay, so such a polynomial is known as the minimal polynomial, which essentially you can term it like this: the minimum number of factors that you need to take from corresponding to each eigenvalue and take a product of that, so that when you generate a matrix polynomial out of this, the matrix polynomial is essentially 0. If you multiply anything further to this polynomial, it has to be 0, but this is the minimum that you require in the polynomial, that so that the matrix is 0. If you, let's say, in this case, in this mj, for example, in this particular example of A that we have taken, if you take lambda minus lambda 1, drop the squared. So let's say you either drop the squared or reduce the cube by 1 power. Okay, so let's say you drop the square for simplicity. If you take a polynomial which is lambda minus lambda 1 multiplied by lambda minus lambda to cube and generate a matrix polynomial out of it by substituting the same A, then it will not give you the 0 polynomial. The moment you multiply another factor of lambda minus lambda onto it, it results in the 0 matrix. Okay, so the minimal polynomial is a monic polynomial where the matrix itself satisfies the polynomial, which means if you substitute the matrix into the polynomial, you get a 0 out of it. Okay, so this is what the minimal polynomial. We'll see how this minimal polynomial comes into use when we try to use another theorem that talks about the matrices and its corresponding characteristic polynomial. We'll stop here. Thank you.